one quick thing I wanted to point out is if you haven't already seen it, is on GitHub, my repo for the class. I've added a few things. Yesterday I added a manual, the C64 Programmer's Reference Manual, and also a D64 to go with it that has most of the examples from the Programmer's Manual actually typed out, so you don't have to type them yourselves, which is kind of clutch. Yeah, so we're going to be using that today. So that's where you can get to it. So let me go ahead and get Vice open. Manuals. Okay, I should not have heard that through. It means the audio is not correctly set up. Hang on one second. Okay. So I'll put the reference manual on one side of the screen and Vice on the other, and we'll use that today. So what I'm going to do is attach that disk image on Vice, and you'll notice that we have if we list the directory contents of it, oops, let me get back on here. Then there's a whole bunch of things, and they correspond basically to which page the program starts on. There are a few of these where, so for example, there's this page 187B, and there's also page 187. There were a few places that I found typos in where what's in the book is correct, but whoever typed it made mistakes. And in a few cases, that actually prevents the program from working. So the B versions are ones that I've fixed the problems on as I found them. And they just happen to be listed at the bottom because they were the most recent things that I've added to the D64 file. So anyway, so let me, to get us started anyway, let me turn on Do Not Disturb so that I don't get a billion emails during class. Let me start with the PowerPoint and just kind of talk a little bit big picture. The PowerPoints, by the way, I have a directory called Slides, and I'm putting copies of them there as we go. So anyway, all right, so let's sort of start to talk some of the graphics, which we've done a little bit of, but I want to keep going with some of it. So the chip that handles graphics on the Commodore is called the VIC-2. And the VIC-20 was the predecessor machine that Commodore made, and it had a VIC chip in it. And so this is kind of a second version, an updated version of it. And it can do a lot for, being early 80s kind of hardware. And we'll talk about a lot of the different functions and things you can do with it as we kind of go through. We'll do the same thing for the sound chip later, and kind of learn like what this machine is capable of doing. So the VIC-2 chip can see basically only 16K worth of memory at any given time. And which 16K of memory it can see is determined by a couple of bits of this particular memory location. And by flipping those bits, you change which 16K is sort of within its window. The default value is 1-1, which actually they're laid out a little backwards than you'd think. But the default allows the VIC-20 to read the first 16K worth of actual computer memory. So 00 all the way through 3FFF. And within that video memory, there are certain subsections that are allocated for different things. And the screen memory, for example, is its default location is 1024 through 2023. So last time when I was poking 1024 comma something and we'd see like the letter A appear at the top left or whatever, what we were doing, right, was just writing to screen memory to say what thing do we want in that particular part of the screen. And the screen memory has 1,000 locations in 25 rows by 40 columns, okay? And the locations are, this isn't 25 pixels by 40 pixels, because that would be way, way, way too small, right? It's 20 by 40 or 25 by 40 things, each of which is 8 by 8 pixels. We'll talk about that in a minute. And each location can display a character from a bank of 128 different characters, and then there's sort of 128 reversed ones where it basically just switches background and foreground. But yeah, so that's what actually lives in this 1,000 things, is if you put a 0 in a spot, it's going to load character number 0, and whatever symbol is in character 0's segment in memory, which is someplace else, is actually what goes to the screen. Okay, so just to demonstrate, for example, if I poked, well, here, let me get me some. Let me just clear the screen. Okay, if I poke 1024 with a 0, then what appears at the top left of the screen? The @ symbol, and a 1 is an A, 2 is a B, and so on. Okay. Now, one thing I want to point out, and we'll talk a little bit more about this in detail in a moment, is if you did this exact same command, in fact, let me just demonstrate it for you. Right? Same machine, right? Okay, it appeared. But not always does it actually appear there because the color may not be set for it to appear. Okay, so in order to make things appear, you actually have to worry about two memory addresses, the screen memory and the color memory. Okay, so if you poke something like, let's say that let me try another spot. Oops. I hit the wrong button. Oops, I needed a comma. I meant a comma, not a period. Okay, it turned into an E. Okay, but if I poke some other location, like, oops, well, how about I do 1100, and I'm just making up this number. Okay, sometimes when you poke that memory address, you don't actually see the character, and it's because it's there, but its color is just set to the same as the dark blue, and so you don't actually see it. Okay, that drove me crazy last year when I'd forget about the color memory. Okay, so let's go back to the emulator for now. Okay, so does that make sense? Right, and this is the part we talked about last time was poking character memory. I mean, screen memory. So how are you going to do the print without print? Or what's the sort of key part of that assignment? Loop through all the characters that are inside the file, but once you get a character, like let's say you get the character and it's the letter A, what do you have to poke to the appropriate location in screen memory? You'd poke a 1 for the letter A, but which location is it and which value do you poke? That's the part you got to figure out. Okay. But that's basically how you can write text to the screen without actually using the print function. Does that make sense? Okay. And yeah, it's obviously going to be a loop, right, as you go through this. Um, the other thing is you guys will have to realize, though, in the same way that when we did like two upper or two lower or the SpongeBob assignment, depending on when you guys took 241, right? You had to, how did you convert an ASCII number to lower or uppercase, right? There was an offset. Well, it's kind of the same problem here, except the offset is not what you think it is, and you have to look at the manual to figure it out. Okay. Um, yeah. There was one other thing I wanted to mention. Oh, with that assignment, you may use the print function once at the very beginning, basically to just clear the screen. So there is if you print a certain special thing, it will just wipe the screen completely. Do that as your first line of your program, and that way it's ready to go when you start printing things. You don't have to erase the screen before you get started. So that's just for convenience. It's in the assignment, yeah. In the assignment file, I put what that one print command is. And that's just for convenience. So feel free to use that. The other thing is you can assume here that the file that you're going to be printing is not too long, right? So that you're not going to overfill the screen, right? So I think what I did was just steal part of the lyrics from Old Wabash and put those in a text file. And feel free to use that as just sort of a demonstration text file, right? If it works on that, then you're good. Okay. Um, okay. So let's go back to the PowerPoint. Um, Okay, so we said screen memory, that's what we were just writing to there, okay? Now, character memory, okay, is different than screen memory. Screen memory just says which character, like basically what you're doing is putting in kind of a reference to the character. So if I put a 0 in a spot on screen memory, it's telling the VIC2 chip, I want you to put character number 0 here, but then where character number 0 is defined is elsewhere in memory. So it's sort of a little bit indirect referenced, which is annoying, I realize. Okay, now the where the characters are located in memory, okay, depends on which of the 16K banks you've basically said, hey, graphics chip, you may use this 16K. The default is that all of the characters are located starting at 6144, which is hex 1000, up to whatever, okay? You can also move it to 1800 through 1FFFF. That's not actually where the characters are, it's just where the VIC goes to see them, okay? Um, and so I know that seems a little bit kind of weird that there's all this sort of dereferencing thing. But also, the reason that this was done is because um, a cartridge would load, like if you plopped a cartridge into the back of the machine, typically the cartridge's memory address starts at 8000 hex. And what that means is you lose basic, but you keep all your characters and stuff. So your game doesn't have to define its own character set, for example. Um, okay, so, and I want to make a demonstration of that using something out of the manual. Okay, so what this character memory business is all about. Okay, so is that okay for right this instant? Yeah. And this will sink in after you read a bunch of the manual. Okay, so let me get him here and him here, and let's go in the reference manual to the graphics stuff, which is starting on page 99. Oh, hang on, it's not loading the whole thing. Okay, let me move this and I'll put it over here. Okay. Okay, so the video banks, here's where you can set those, okay? Um, and screen memory, we'd already talked about that. You can change the location of screen memory by adjusting stuff. We'll leave it at default for now. Um, and color memory cannot move. It's always located between this range and this range, okay? Um, so if I wanted to change the color of, let's say 55296 to, let's say 5, that changes the ampersand from the light blue to this sort of light green or whatever, right? So I'm not changing what symbol is there, right? So I didn't change what was in um, address 124. What I changed is what's in address 55296 or whatever. So the character gets loaded in, and then a color is sort of applied on top of that. But they're separate things. Yeah. Yes, it's okay. So that is when I poked 5 there, what I was basically doing was only changing the bits, well, that correspond to the color, right? So that character in memory is actually a black and white thing, right? And if you think about it's in binary, right? So, and I'll show you how this works in a minute, but whether or not it's background versus foreground is just a 0 or a 1, right? So the character's graphics itself is an 8x8 grid, and I'm just choosing which pixels are going to be foreground and which ones aren't. What color they get displayed in is separate, okay? And what this, by stripping out the two things, you actually save memory, because I can say, okay, I only want to store the shape here and the color over there, rather than putting them all together. That would take up more space. And we only got 64K of it, right? So we got to be a bit efficient. Is that okay? This also means that actually the colors, and here's why, the other reason they did this, the 16 colors that you have at your disposal are fixed. They are hardware limited by the graphics chip. Okay. If you don't like those 16 colors, you can pound sand. Okay. That's all the hardware can do. Right. So why spend a bunch of bits to define in terms of red and green and blue all these colors when you can't have any more than these 16 anyway? Right? So if you only have the capability of doing these 16 colors, you only need 4 bits to store that information, right? Because 2 to the 4th is 16. That saves a lot of space, right? Now, is it as good as a modern machine? Like, let's say where you've got, if you use 8 bits per color, 8 for red, 8 for green, 8 for blue, that gets you, uh, 255 cubed, whatever that number is, number of colors, right? That's still not a whole lot. Night and day over this, but this is in the early 80s, right? So, and the Nintendo, by the way, was pretty similarly limited in terms of its color selection. It was a little bit better, but it also had some kind of weird. It could do more colors, but you couldn't do all of them at the same time. Was one of its limitations, which is kind of crazy, but yeah. Okay, so does that make sense though? Yeah. Color is separate from the shape itself. Okay? And by the way, the shape itself has nothing to do with how BASIC treats it. Okay, so the fact, like, if I wrote a BASIC program in green, should it work any different than if I write the BASIC program and it's in blue? No, the same characters, right? And in fact, if I change the graphics for the letters to make them look different, BASIC will still treat them as the same thing. It's all about how they're displayed versus what they are, right? Which is a little weird, but yeah, okay. So let's carry on. Okay, so color memory. Now, the character memory, okay, normally where the characters are located is actually controlled by is ROM, okay, meaning that I can't change what the characters look like because they're being generated by a read-only chip. Okay, so if I want to change how the characters look, I have to do two things. I have to first change where in memory the characters are going to be, graphics are going to be stored, and then change what's there. Okay, so I can't just change what's on the ROM chip because it's a ROM, not a RAM. Is that okay? Okay, so for example, let's suppose that I do this command right here. Okay, so let me just type it. 53272, and I'm going to poke that with the result of peaking 53272, anding 240, and ORing against A. Okay. All right, so what happened? Well, I don't know. It doesn't look very good. Okay. Yeah, we've entered the matrix. But you'll notice that, well, a couple of things have happened, right? So what I've done is I've changed which, well, and I never defined A here, so yeah, because A is going to be one of those values there. So let me reset it and remove the or A part deliberately, and I'll show you. Okay, so I'm going to do a soft reset, and let me do it one more time. So let me poke 1024 with a 0 like before, and then let me do, I'm going to do, let's see, what was it? Poke 53272 with the result of peaking 53272, anding against 240, and then I'll just leave it at that. Okay, so it's basically what we saw before, because I never defined what A was, and so it was 0, and hence it's like I didn't do anything. Okay, all right, so what do we see there? Yeah, okay, so you see where the cursor is, right? It's still in the same spot that it was, and we can see it blinking, okay? Um, the color is still the same as it was, but what the cursor looks like has gotten all messed up. And for that matter, all the other locations on the screen, okay? And because what's happened is character memory, right? We've basically said, hey, VicChip, I want you to use basically the bottom chunk of memory from 0000 through 7FF as where you're going to go look to get the actual character symbols. Okay. And you guys see how there's a bunch of stuff that's kind of flashing and flickering? Okay, the reason that that's happening is because those memory addresses are being changed. And so if I'm using those to draw graphics and what's in those memory addresses is changing, what I'm going to see is going to look different. Okay, so for example, you see the top left corner, how it's got, kind of twitching out a little bit, right? The reason that that is happening is because that actually corresponds to memory addresses that are like, well, like memory address 0, right? Memory address 0 is going to define here what appears, what that top left figure looks like, and it's all janky because memory address 0 is actually being used by the computer to do internal computations. Okay, so the cursor blinking, like things like that. The computer's not just sitting there; it's doing stuff. Okay, and it's like waiting for keyboard input and what blinking the cursor. All of those things are happening, which means it's got to be changing memory as it does stuff, and we are visually seeing that here. Okay, is that all right? Okay, so I would never actually change the location of character memory to this particular subaddress. That would be a bad decision. Um, but I showed it to you to illustrate why it's a bad decision. Okay. The other reason why it's a bad decision has to do with the memory architecture on this thing, or on the 6502 process, which I'll sketch out in just a second. Okay, so I've not changed what's in screen memory. I've also not changed what's in color memory. What I've changed is where in memory, screen memory points to the actual letters. Okay, is that okay? So if I wanted to change, like, let's say I wanted to make my own font, for example, this is how I would do it. I would change the screen, or sorry, the character memory to be in a certain segment and then load in all the way I wanted my letters to look in that segment of memory. Okay, is it okay? And we'll continue with this. Okay, because there's another example that I think will be a little bit more illustrative. Okay. Um, and namely, let's look at, let's see, which example is it that I wanted to do? Let's do this one here, page 110. Okay, so let me reset the machine so we can actually see what we're doing. Okay, and I'm going to load page 118 or 110, sorry, from the disk. Okay, and there's the program. Here it is. I'll kind of zoom in on it. Okay, so what it's going to do is it's going to print a special character to switch to uppercase. Okay, great. It's going to poke some things to reserve some space for character memory. Okay, it's going to turn off the key scan interrupt. Basically, that's what is, we'll talk about interrupts later, but like much later. It's basically how the computer is monitoring for us to hit things on the keyboard. If you turn that off, your programs will run faster because it's not wasting time looking at the keyboard to say, hey, is something being pressed? But then obviously you want to turn that back on when you finish your program so that you can still type stuff when you're done. Okay, so that's just to make what it's going to do a little faster. And what it's going to do is basically copy some stuff in memory, okay, from one place to another. Okay, so let me run it and let's see what we get. Oops. Okay, so it's running, right? I don't see the cursor. And when the cursor comes back, I know I'm finished. Okay, nothing happened. Nothing appeared to happen. Okay, so you remember when last time, when I ran the previous command, everything was all janky, right? Here, what I did, or what they did, was first I copied all of the characters out of ROM into the new location. And then I said, okay, use this new location for where you're going to get your graphics. We don't visually see any difference because I just made a copy of what the defaults were, but I've changed where I'm pointing to them. By moving them, I can now change how they look. Okay, so for example, what is one of the things that um, we poked? So let's see. Well, let's look at our loop, right? What have I done now? How many things have I copied? Oh, and what was that? Let me change the so that it's a little easier. Here, let me list it again so it's easier to read. There, that's better. Okay, how many things, what have we done in our loop, right? The loop is on line where? Yeah, line 40 is basically our loop. That's where the meat of this program is, okay? And what that is doing is basically saying, all right, I'm going to copy 512 bytes worth of stuff. Yes? Okay, now where am I getting this stuff from and where am I poking it to? So what's the first location that I start getting it from? 53248. Okay, and what is I? It starts at 0, it ends up as 511. Okay, so hence 512 bytes. So the very first memory address that I'm going to look at is what is in memory cell 53248. Whatever I find there, I'm going to copy it just wholesale to memory address 12288. Okay, and what was in memory location 53248? Well, let's see what's there. Okay. Yeah, okay. Is that all right? So, yeah, so what is in memory cell 53248? Let's find out. Okay, so what could I do? I could print the result of peaking 53248. Okay, and I get 0 in this case. Okay, and what's in the next one? So I hit enter. Also 0. That's interesting. Oh, don't tell me they're all zeros. That would be kind of a bummer. Oh, okay. Well, whatever. But, well, or let's look at the destinations and see what ended up there. 12288. Okay, 60. 12289. 102. Okay, so on. All right, what do these numbers mean is really the next question. Okay. Okay, so if we look back at the example, okay. Oh, sorry. We need to do, I forgot one other thing. We need to do this 53272 with peak 53272 and 240 plus 12. Okay, so that command, right, what happened? It's the same thing as what happened before, right? And I don't think we wanted plus 12 there. That may be a typo. So let me look back at, let's go back up to this sheet here. Where was the destination that we were copying stuff to? It was like 12288. Okay, so I needed to OR it against 12, not add 12. Okay, so let me reset, load page 110. Okay, so I'm just rerunning that program. Okay, so let me do, what did I say I wanted to do? I wanted to OR it against 12. Okay. Okay, so let's do poke 53272 with peak of peak of 53272 and 240 or 12. Okay, basically nothing happened. Except, what do you notice about my cursor? Huh? It's a little different. And also, for that matter, what do you notice about right here? Looks a little bit different, okay? Right? All right, so everything looks exactly the same. So that must be, that's a typo. This right here should be or 12, not plus 12. Okay. And that actually makes sense, unless I made a typo the first time, which I could have, but I don't think I did. Okay, so what I've done, right, is I've copied the contents of memory that had the graphics to a new spot. And then with the command that I added that was after my program, I told the chip, go get the character stuff out of the new spot rather than the old spot. Now, because I had copied everything, it all looks identical. The cursor maybe being the one exception here, okay? But I could change what's in memory. So for example, what is currently in memory address 12288? 60, okay? What would happen if I changed that? So what about if I poke 122288? Well, okay. It's in decimal, yeah, it's 60. Okay, so, but really, when I'm peeking from a memory location, what am I doing? I'm asking what 8 bits are in this memory location. If I print that, then how is BASIC going to print it? It's going to print it as a number from 0 to 255 because it's an 8-bit number, right? And that's all we can do. Now, BASIC prints it in base 10 because it's BASIC, right? So what is that in hexadecimal? I don't know. We'd have to do the conversion, right? But that number from 0 to 255, that's what's actually in that particular byte of memory. Okay, so good. All right, so let's poke something to that memory location. And before I do it, actually, let me actually do. Poking is what, yeah, so peeking says, hey, what's in that memory location? Poking it puts data into that memory location, right? That's why they gave it the name peek and poke, okay? So let me type, well, let me actually do this. Poke 1024 with a 0. Well, okay, let me do it again. All right, what's in the top left corner? An ampersand. Okay, and let me poke while I'm at it. What was the base address of the color memory? Sorry, I always forget these addresses. I did. Screen memory, color memory. 55296. All right, so let me do 55296 with a 5. Okay, so now we've got that green ampersand. Okay. All right, then let's do, let's poke 12288 with, pick a number, of course. Oh, okay, we can't see it. Okay, you see the ampersand there? Does that look right? Not quite, right? It looks fine except for the top bit of it. Yes? Okay, well, let's poke it with something else. Okay, give me another number. Huh? 40, what was it? 42, of course, yeah. Okay. Looks a little different. Yeah? And let's kind of keep this gravy train running. poke it with 0. What happens? What happened to the top row of it, or the top bit of it? It's gone, okay? And just as easily as I can make it all go away, I can make it all be on. You guys see where this is going? It's not a fraction, it's in binary. Yeah, okay. So I've screwed with here the first byte of it, and there's 7 more, okay, that I could mess with. So here I've been poking 12288, but what would happen if I poke 12289 with a 255? Oops. Yes. Okay. But it's not changing that it's an ampersand, it's just changing how the ampersand looks. Okay. So if there are any other ampersands on the screen, for example, let me put one up here, it has changed that. But if I poke this, well, let's just keep going. Let's do 290.255. Okay. It's in this case, because I'm poking 255, it's filling it in. Okay. And if I poked it zeros, it would disappear. Okay. Is that okay? All right. So what was it originally? It was 60, I think, right? Okay. Let me draw a diagram to indicate how these things are actually being used by the machine. Okay, so would I actually want to poke 255 in this case? No, because it's making an ampersand not look like an ampersand, right? Um, but so let's see, 371. Okay, so let me go back to let's go iPad here. Remember last time we were talking about how the screen memory's value is pointing to a section in character memory that corresponds to the actual character itself. The ampersand, we're looking at 0. Okay, so we're looking at the 0th character out of the character set. And characters are all, let me sort of draw a picture here. A character is 8 bytes. Okay, so we set 255, 2, 3, okay, we set 255 to be one of those bytes, right? Which means well, actually, you know what? Let me go back and let me change it to, let's do the original value that you guys picked, which was, well, actually, let's do what it started with, which it happened to be 60. Okay, good. All right, so 60 in binary is what? Can I fit? So the place values here are those, right? You guys remember that? It's been a hot minute for a few of you guys. All right, can I fit any 128s into 60? No. So I get a 0 there. Can I fit a 64? No. Can I fit a 32 into 60? With how much left over? 28. Can I fit a 16 into that? With how much left over? Huh? 12. Can I fit 8 into that? Yes. With 4 left over, 4 like that. Is that what we saw on the screen? It is. It's exactly what we see. Huh? Where should you be looking? Look at the top of the ampersand. Okay? 2 pixels on, 4 pixels on, 2 pixels off. Corresponding exactly to those bits. Right? So when I poked with 255, what was I doing? I was turning all of those bits to a 1, and we saw all 8 pixels. If I turned it to a 0, what would I see? None of them. Okay, so if I continue with this game, okay, so what was that address, 12288? And the value there was 60. Okay, then if I look at the next address, so the next address, you see how it has the, it's all solid? That's because I poked it with 255. What would be a better value to poke it with? Well, let's try 60 again, actually. Does that look good? No, in fact, let me poke this one with 60. Not quite right, right? Okay, so I poked it with 60, which means it looks like exactly what was above, but that's not quite right. So let me come back over here. What do you think would be quite right? Well, probably a 0 here and here, right? Well, let's try this. I've written the number now in binary. What is its equivalent base 10? So what do I got? I got a 64 plus a 32. That gives me 96 plus 4 is 100 plus 2 is 102. Okay? All right, now, do you see how I'm kind of looking at this? I don't think my fancy pants thing can do this. No, that's the eraser. Oh, no, here we go. Here's how I'm looking at it. Okay, so what did we say that the number was? 20 or 10, what was it? 102? 102. Okay, so let's go back and let's poke memory address 12289 with 102. Does that look better? No, I think it looks worse. What do you guys think? Yeah, okay, so I probably botched it. What should it be? Well, let's look back to where were we copying all this from in the first place? Let's look at address 53249 and see what's there. Oh, there's no way it's 0. No, so I've run into this before where it's, let me do this. Let A equal peak of 53249. Oh, there's no way it's actually 0. Um, no, because it's coming off of ROM, so it should not be destroying the source. Yeah, because and again, if we look at our program, um, then oh yeah, okay, no, that's another problem. I'll come back to that later. Um, Point being, though, it's not what I put is not the correct value. Okay, correct value to make it look like a correct ampersand. Okay, um, so we've messed with 3 memory locations here and made our ampersand look kind of janky. And like, how am I going to figure out what it should be? Well, if I go back to here, right, think of what I'm doing is I'm drawing an 1, 2, 3, 4, 5, 7, 8, 9. Okay, you know what? Let me not be stupid about this. If only we had a program that was designed for making tables on our computers. Wouldn't that be excellent? Okay, so let me blow this up so it's a little bit easier to see. Okay, so what I'm doing is I'm saying, what was the first address? 12288, 12289, 12290, 12291, and so on. And then I'm going to make this these 8 ones, and I'll make it 24 pixels this way and 24 pixels this way. That doesn't look the same. There we go. Okay. And so what I'm doing, right, 6, 7, 8, is, let me put the grid. Oops. Okay, is 12292, 12293, 12294, 12295. Okay, so I have these 8 bytes, and I'm thinking of them in rows, and I can make my graphic look the way I want by setting each of these 64 pixels to be either on or off. Okay, and if I choose them to be on or off in some sort of useful pattern, it's going to look like a letter. It doesn't have to look like a letter, but at least what we've done so far with all our programming, it always looked like a letter. Okay, does that make sense? Sort of? So, if it's not going to look like a letter, then what? What could I make it look like? Okay, sure, symbol. And I could put Greek letters in here if I wanted, right? But I could use this to make graphics, right? Because if I can control that in this 8 by 8 grid, things that are a 0 will appear in the background color, and things that are a 1 will appear in that grid's foreground color, I could draw with it, right? Because every location on screen corresponds to, it's in one of these 8 by 8 blocks, and I just need to figure out which block I'm in and change the appropriate bits. Yeah? Okay? All with characters. It's kind of crazy. All right, so let's go back to the emulator. Okay, so the example they give here is to, let's see, where did they do it? Here is it, all it did was they made it flip vertically. So they switched all the ones to zeros and all the zeros to ones, and that made it sort of look like a reversed image. Okay, so basically what I've drawn here in on Excel is this grid, right? Where the ones are is going to be the foreground color for that particular grid, manipulatable using color memory, and what's a 0 is the background color. So draw whatever character you want, and then figure out which byte, like the top row is 1 byte, the next one's the next byte, and so on. Okay, is that kind of cool? Yeah. All right. So where you can go with this is kind of clever. And let me go back to the PowerPoint for the moment. We talked about color memory, and here's the character stuff, right? So the letter A is by default located in that location. So if I looked at D1000 through D007, that's where I would have seen what the ampersand should have been. Okay, but the reason I'm getting zeros is because this program switched out that thing of memory. So it's essentially disconnected the character ROM. So I copied the data, then I turned off the ROM that it was coming from, which is why I'm reading zeros if I try and read there, because I'm now reading from actually something in RAM, which was zeroed out because I, just turned the machine on. Yeah. No. ROM by definition means what? Read-only memory. So you can only read from it. You can't write to it. So that's why we had to copy it first and then turn off the ROM. So that, but the copy is now in RAM so that we can modify it. Okay. The only other way to do that would be to open up the machine, pull out the chip, and put a new one in that has a new ROM on it. Okay. Yeah. Oh, we can't. Okay, we can. Let me back up. Part of that program basically said, okay, in this segment of memory, you can either have the ROM chip connected or you can have more RAM. And it switched it so that the ROM chip was disconnected and we have more RAM. So if I tried to read from that RAM, well, nothing was there in the first place because it was just powered on. And so of course I'm going to be getting zeros, right? So that's why we were getting zeros, is because well, I've got some more RAM, but in some sense have I actually gained any RAM? No, but I gained RAM when I disconnected the ROM, but I still needed all the characters and I just had to copy them elsewhere into RAM. Okay, so in terms of my net amount of RAM that's free and unused, nothing, right? I haven't changed anything. All I've done is change where I go or where the graphics chip goes to get the actual character art. Okay, that's it. Okay, yeah? Okay, so there's a formula then that we can use to figure out where we are on the screen, okay? And page 111, that's basically just the example we just did, okay? And I'll come back to multicolor mode, but let me just show you guys an example as preview of coming attractions, then we'll dig into the details in a little bit in a moment. Okay, so let me go back to here and here. All right, we'll look at that example because it's kind of fun. So let me reset the machine and undo everything we've just done. All right, page 114 from disk 8. Oh, and let me change that. Okay, so it's a pretty long program. In fact, you can't even read the whole thing in one go. Okay. The other thing is, and we'll come back to this, you see how it's got all these data statements? You can actually store data within a program and use it rather than having to access an external file. For some things that's useful. But if I run this program, let's see what it does. So what did it do? Okay. It made what looked like a cat. How did it do it? Okay. It did it with pixels, right? So when we saw that it was blank for a little while and just sitting there before it did anything, right? That was it copying the character stuff from the chip onto someplace in RAM. And then it modified 4 symbols, the less than, equal to, greater than, and question mark. Then it put a less than, equal to, greater than, question mark on those spots of a blank screen. And because it had modified those characters, it looked like a cat instead of a less than, equal to, greater than, and so on. Okay? And then what happened is it basically, if I don't hit a key, it just sits there. Okay? So what it's doing right here on line 170, get a $sign, that's getting keyboard input. If I'm not hitting a key, it's just going to sit there. And if I don't get anything, it's going to just go back and keep checking. Hey, have I hit a key yet? 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 And once I hit a key, then what does it do? Moves on from line 180 to line 190. And what does that do? Poke 53272 with 21, return to normal characters, right? So it switched us back to the normal set of characters instead of the modified set. Okay. Now in this case, it only modified the 4 of them, but it could have modified all 255 of them, right? And made a cute little cat in the process. Okay. It gets better. Okay, so you see how we still see stuff, right? So it's messing with the color memory. It's also copying things, and it never turned off the keyboard interrupt, which is why it's going so slow. But then it'll go a little faster here. Isn't that cool? How is it doing all of this? Oh yeah, there's a big for loop, right? So it's using, BASIC has a routine that can do sine of an angle, okay? And it's calling that routine over and over again, but it's changing bits from either a 1 to a 0 or a 0 to a 1 that correspond to where the plot is on the screen, and it's changing them in character memory of wherever that thing appears in the screen, and then we see it as dots on a screen making this beautiful looking sine graph. Okay, all with color memory, or I mean with graphics memory, right? And if now I can't use the machine anymore because it didn't put them back. Okay, so I would have to reset the machine in order to do something else with it. Let me just do that, and let's look at the code. It's actually a pretty short program. Okay, so let's just kind of look at it and see, well, what's going on here? All right, base equals number. Okay, it's just defining a base address, no big deal. Okay, poke 53272 with the result of peaking or A is changing a graphics bank. It's also doing something else on line 10, sort of similar. For lines 20 and 30, right, what it's doing is basically copying, zeroing out memory. So it's zeroing out 8K worth of, well, is it 8K? 8,000 sections of memory, okay, with zeros. And then it's poking 3 to the screen, that was where all the blue bars went across. That was the faster one, okay? And then line 50 is setting up a loop where I'm going to count from 0 to 319 in increments of 0.5. Okay, this is actually kind of cool. You guys remember in Python, how does the for I in range function work? Do you have to always count by ones? No, you could count by twos. And in BASIC, you can count by 0.5s. Okay, that may seem a little silly, except why counting by 0.5s is actually a good thing. And what's so special about the number 319.5 or 320 for that matter? How many pixels across is this screen? 320. Okay. So that's why they did it that way. Yeah. Okay, so it's going by every 0.5 unit. And then there's some sort of gobbledygook going on here, namely it's computing the y value is going to be the result of getting sine, and then also there's an offset here. And so this part here, dividing x by 10, what does that change about the sine curve when you modify what's in front of the x there? It changes the frequency, right? So if I divided it by nothing, it would cycle a lot faster, okay? And if I divide it by a bigger number, it would make it cycle slower, okay? So that's the frequency control. What's the 80 in front of the thing do? Like, so this is back to high school trig or algebra. It stretches it vertically, right? So instead of being a tiny little sine curve, it's a really tall one. And then the 90 plus that's in front of it just shifts it up on the screen so that it's centered at the middle of the screen instead of being centered at the bottom or top. Okay, does that make sense? Okay, so that's all just graphics, right? What function do I want to graph? And then what's going on lines 70 through 90 is basically, if I have a location on screen, how do I know which character corresponds to that? Well, I got to do some math, right? So for example, when I was messing with the ampersand, how did I know which byte to go to? Well, in that example, I didn't. I just kind of winged it, right? But if I didn't know how to wing it, then I would have to do some math basically, and the formula basically is there, right? Is that I get my x position and my y position, and then I do row times 320 plus 8 times character plus line, and that will get me to the appropriate byte, and that tells me where I need to poke the data. Okay. The book actually has a diagram that makes it clear why that's the correct formula, or book / manual. Okay. And then I'm just poking something, and that's it, right, to make the graphics look cool, and then repeating the loop. By the way, on line 110, what's that weird symbol that, yeah, what does up arrow mean? It's just the exponentiation. Okay, so like we would type this with a caret nowadays. Okay, or in Python, how would you do exponentiation? Star, right? Back on this machine, and you can't see this when you're doing it in Vice, but if you come look at the physical keyboard, there is actually an up arrow key on the keyboard. Okay, so you would have used that to do exponentiation on this machine. The star thing hadn't been invented yet, I don't think. I mean, certainly Python hadn't, right? Because this machine predates Python by about 10 years. So, okay, so that's kind of cool, huh? Yeah. All right, so we'll continue with more graphics on Thursday, I guess. Oh, sorry, there's one other thing I forgot to mention before we quit. So your professor's an idiot, okay? And in particular, your professor forgot about 2 programs that are included as part of Vice. Let me just full screen this. So there are two programs, console programs, that are included with Vice. One of them is called C-1541, which will allow you to add files to D64 files and get data out of D64 files. What's the other option that we have for moving things to and fro a D64? The Droid program, right? Droid 64. What's the benefit of Droid 64 versus this? Well, that and it's well, so do you have this one, right? But Droid 64 is GUI, right? It's got a graphics menu to it. Okay. What about the C64 list program that you Mac users have to have Wine to even get to run because it's a Windows executable? Do you need that? No, of course not, because you can run PetCat, and PetCat is capable of converting between Petsky stuff or programs and regular old plain text. Okay, so let's say that I typed out a basic program in VS Code or whatever, and I need to convert it to a tokenized form so I can load it on my Commodore. I could use C64 list, but I could also use PetCat. Okay, or for that matter, I could also use Droid 64 for some of that, right? So we've got lots more programs in the arsenal for dealing with these squirrely data types. Yeah? Okay, now we will quit. And you can read the manual. So, all right, see you guys Thursday.